Hello everyone, welcome to the third course in the HCI IoT course series. In this course, I will introduce IoT security technologies. Security has always been the basis of technological development. Only by ensuring the security of a technology can we develop it well. This is especially true for the IoT field, because all the things are connected in the IoT world. IoT development will be restricted if we can't resolve security issues. In this course, we will learn about the problems faced by the IoT, Huawei's solutions to IoT security problems, and typical applications of these solutions. First, let's take a look at the problems encountered by the IoT in the security field. The first event we are going to talk about is the Tesla incident. I believe most of you have heard Tesla. It is the most successful company in the electrical vehicle market. Although Tesla is unrivaled in self-driving, it faces substantial security challenges. Either electric vehicles or self-driving will be used in Internet of Vehicles, which is one of the IoT applications. Therefore, security issues of the IOV are also related to the IoT. In this incident, when the in-vehicle system is intruded into, the attacker can remotely control the starting and stopping of the vehicle through the network. This is extremely dangerous if the vehicle is driving. The cause of the Tesla incident is that no protection is provided for local storage of key information. Anyone who knows the background remote communication certificate and password can obtain the in-vehicle system login password to control the vehicle. Besides the Tesla incident, some IoT-related security incidents have occurred in China. One of them was the Nanjing Environmental Protection Bureau incident. In this incident, someone intercepted and tampered with environmental protection data at the near end of the network, causing the uploaded data to be displaced as qualified. All the indexes displayed on the monitoring platform of the Environmental Protection Bureau were normal, while the cement plant's pollution levels significantly exceeded the allowed limit. The cement plant evaded sewage charges worth millions of dollars through forged monitoring data, causing serious environmental damage. The cause of this incident was the encryption and integrity protection were not carried out during data transmission from the gas detector of the cement plant to the RTU remote terminal, which allowed the violation to be possible. This incident occurred at the network layer of the IoT, in the form of tampering of environmental protection data through network intrusion. There have been other security events at the network layer. For example, the DDoS attack event. DDoS, short for Distributed Denial of Service, is a common type of network attack. Attackers control a large number of devices to attack a server, causing it to break down. As a result, users cannot use the server. Let's look at the DDoS attack in the US. This attack was mainly launched using a botnet composed of IoT devices. In this DDoS incident, hackers controlled some IoT devices like network cameras, video recorders, and routers. This incident paralyzed the internet and caused network outages in several cities in the US. As you can see, in the IoT field, security is a common issue that deserves our attention. Examining these three events, we can see that IoT security issues often occur on the device and network sides. Actually, they also occur on the platform and application sides. We classify IoT security issues into 4 types based on the IoT architecture. In terms of industry categories, security threats mainly include LPWA security threat and IOV security threat. As you can see, IoT security threats form a negative triangle model, and most of threats are on the device side. While we lack effective measures to defend against the security issues, IoT devices are vulnerable to physical damage, for example, being forcibly dismantled. Because of power supply restrictions, it is not possible to run an advanced encryption system on IoT devices. Due to these 2 reasons, IoT security threats often target devices. Moreover, as network technologies become increasingly advanced, more network attack technologies are emerging, and the requirements for the capability of network attackers are become lower. In the past, attackers needed to master a lot of knowledge to launch network attacks. Nowadays, attackers can launch attacks with limited communications technologies. IoT security events increase alongside the development of the IoT. This requires us to resolve IoT security issues while developing the IoT. How can we solve the problems mentioned above? Let's see what solution Huawei provides. I will introduce the overall architecture of Huawei's IoT security solution. First, let's take a look at the framework of the Huawei IoT security solution, which can be summarized as 3T plus 1M. In the 3T plus 1M framework, T stands for technology and M stands for maintenance. The 3T indicates the different security technologies at the sensing layer, network layer, and the platform layer in the IoT architecture. And 1M means unified security O&M at each layer. This framework illustrates the measures that Huawei uses in the IoT security field. It is based on the summary of threats in key IoT security fields. The IoT security solution is focused on LPWA and vehicle, which is IOV. Since most IoT security issues arise from these 2 fields, of course, we also support other fields. As shown in the framework diagram, we provide security applications for the 3 layers of the IoT architecture, from the sensing layer and network layer to the platform layer. We also provide compliance at the bottom. We have different security measures at different layers. We adhere to the concepts of device authentication, pipe monitoring, and cloud analysis. We use trustworthiness and identity authentication of devices, pipe monitoring awareness, and security policy orchestration and collaboration in the cloud to build a service-oriented IoT security solution for customers. We also use unified security O&M and management across all layers to ensure normal collaboration between layers. That's all for the security framework. Next, let's learn about the security measures used at each layer. FOTA, short for firmware over the air, allows us to remotely upgrade vehicles or unmovable devices. At the sensing layer, FOTA digital signatures ensure the validity and integrity of firmware upgrades. We can check the integrity of upgrade packages and ensure that the firmware version in use is secure and reliable. Besides the solutions for the sensing layer, we need to defend against DDoS attacks at the network layer, where our devices are vulnerable. The method we use here is to classify messages from devices by different priorities. If a DDoS attack occurs, the server can then determine how to process messages from different devices according to the congestion level. For example, when a server is in a low congestion state, it allows low priority devices to access the network later or discards low priority packets. This ensures that high priority data can be sent to the server for normal communication. At the platform layer, authentication is used to ensure that each device connected to the platform and all uploaded data are secure. We carry out E2E authentication and transmission security on the platform side. As you can see in this figure, different personnel or devices, such as gateways or devices in the sensing layer, development or O&M personnel, and applications must all be authenticated and authorized through different networks and portals when they access the cloud platform to ensure the security of all devices and personnel. This eventually ensures secure E2E data transmission of the IoT. That's all for the Huawei IoT security solution. Next, let's look at the typical applications of these solutions. Here is a case related to bicycle sharing. A shared bicycle is an IoT device, and it has many security risks. First, some shared bicycles do not use security encryption methods, and authentication may not be required for obtaining passwords, which allows for password forging and cracking. Some shared bicycles may use encryption methods but consume high power, failing to meet battery requirements. To address these issues, we recommend DTLS Plus with dual authentication to improve confidentiality and reduce power consumption. Second, some bicycle platforms and devices may not be collaboratively connected. As a result, many malicious operations on bicycles are invisible to the platform, and the platform cannot identify damaged bicycles so that the operating costs increased. The Huawei IoT platform implements device cloud synergy so that all operations on bicycles are visible on the platform, helping reduce malicious behaviors. The last problem is malicious upgrades of lock firmware. Hackers can use forged servers to upgrade lock firmware and change passwords to gain complete control of bicycles. To prevent firmware and passwords from being maliciously upgraded or changed, Huawei uses lightweight trusted DICE to secure boot and trusted measurement of the running state. In the end, let's make a summary. In this course, we learned about IoT security issues and the Huawei IoT security solution. The security solution uses a 3T plus 1M architecture. In the last section, we learned about the typical applications of this solution. That's all for the first chapter of the HCIA IoT course series. In this chapter, we learned about basic concepts, hierarchical architecture, and major industry applications of the IoT. In the next chapter, we will learn the detail about the network layer. Thank you for your watching. See you next time.